My friends and fellows, to thermal engineering concept and the principal channel. Welcome again, and let us continue in presenting more applications of the wall where there is a heat generation per unit volume within the wall and is exposed to another type of boundary conditions. The physics in a plane wall. In part 4, we will talk about other boundary conditions which are to be applied for the wall and solve the one-dimensional heat transfer rate by conduction, where a heat generation per unit volume within the wall should be considered. Thank you for your support, and let us start with the objectives of the present episode. The objectives of the present video are one-dimensional heat conduction with heat generation, where the heat transfer passes through the plane wall in one direction. We will apply the fundamental boundary conditions for convection and adiabatic on the wall sides to find out the temperature distribution in the plane wall. And then, as usual, we will arrive at the closure for the present episode. Conduction equation in Cartesian coordinate, where energy is generated per unit volume of that domain. The element which has been discussed previously in a three-dimension dx by dy by dz and is exposed to heat transfer in the three directions x, y, and z, and this form of equation has been derived in a previous episode in the form partial square t with respect to x square plus partial square t with respect to y square plus partial square t with respect to x square plus q dot divided by k equal to 1 by alpha partial t with respect to tau. And we said that this equation represents the transient form of heat conduction in a plane wall in the three dimension. In this equation, we have alpha as defined before, as which represents the material thermal diffusivity, and the one-dimensional form for a steady state condition has been derived in the form of d squared t by dx squared plus q dot divided by k equal to 0. And if we have a look at the figure, q is perpendicular to the surface and has the direction shown in the red arrow. So the general form which we have derived before, and we called it the magic equation, which is used in the plane wall experience, heat conduction and heat generation in the steady state conditions, is represented by equation number 4. Of course, this equation will be repeatedly used through this series of videos uh, for applying different boundary conditions.
Now let us consider a case study where a convection boundary condition for the wall uh, where it is exposed to a fluid having temperature Ta and H sub A. And now for the figure or the plane wall which is shown uh, in this illustration, one side is adiabatic, which is insulated, and the other side is exposed to a fluid. And the question is how to find the temperature distribution in terms of the convection parameters. The solution for this uh, case, we should remember the general form of the question for the heat transfer, where in one dimension with the heat generation for steady state, which is represented by equation number 3, d squared T by dx squared plus q dot divided by k equal to 0. And let us consider equation number 4, which represents T of x equal plus q dot divided by kx squared divided by 2 equal to c1x plus c2, which has been obtained from double integration of equation number 3. We have boundary conditions for the insulated side of the wall. We have Q minus K A dt by dx equals to 0, and that will give dt by dx at x equal to 0 equal to 0. If we apply this boundary condition in equation number 4, then we will get C1 equal to 0. And if we consider the boundary condition at x equal to L, and let us consider the temperature there is T sub W, then C2 equal to T wall plus Q dot divided by K plus times L squared divided by 2. And if we substitute that in the general form of equation number 4, then we will get the temperature distribution in terms of the wall temperature and the heat generation per unit volume as represented by equation number 6. If we continue the derivative, we have the heat transfer rate by conduction at the wall surface, which is exposed to convection at x equal to L, equal to the same amount of heat transfer rate by convection at x equal to L, which represents the steady state condition for heat transfer. And if we substitute the values, then we have the conduction part equal to H sub A times delta T, which represents T sub W minus TA. And at x equal to L, if we substitute the values, then we will get dt by dx at x equal to L equal to H sub A divided by K times tw minus t sub a. And equation 6 will be dt by dx equal to minus q dot divided by k times x, and if x equal to L, then dt by dx at x equal to L equal to minus q dot divided by k L. Equation number 8. Therefore, equation 7 and equation 8 produce minus HA times TW minus TA equal to minus Q dot divided by KL. Then we will get T sub W equal to Q dot L divided by HA plus TA as represented by equation number 9. And this will produce, when we substitute the value in equation number 6 for T sub W, then T of X equal to Q dot L divided by HA plus Q dot divided by 2K times L square minus X square plus TA, which represents the final solution for the temperature distribution for the wall, which is exposed to convection and one side is insulated. For verification, dt by dx equal to minus q dot divided by kx, and if we have x equal to 0, then dt by dx equal to 0. And if x equal to L, then T sub W equal Q dot L divided by HA plus T sub A. And these are the boundary conditions which has been fulfilled by the general form of equation number 10. And now let us derive an expression for the maximum temperature in the wall of the previous case study, and that means when the wall is exposed to convection and it's insulated as shown in this figure, then we will need to find the maximum temperature, the position of that value for the maximum temperature and where it is. And the general form is again d square t by dx square plus q dot divided by k equal to 0, which represents the one-dimensional heat transfer in the plane wall where there is a heat generation and a per unit volume under steady state conditions. We have equation number 10 as represented in the previous example. Then we may find the maximum temperature from equation 10 by visual evaluation. For this equation, the maximum temperature occurs when L square minus X square is maximum, since all other values are constants value. Temperature of the wall, Q dot, thermal conductivity, the thickness of the wall, heat transfer coefficient, all of these parameters are constants. Then maximum temperature depend on L square minus X square as a maximum. And if we have X equal to 0, then this value L square minus X square equal to maximum. And then the answer for Tmax equal to Q dot L divided by H sub A plus Q dot divided by 2K L square plus TA. This is the answer for this example. And another way is to get the maximum temperature by taking dt by dx equal to 0. And if we take dt by dx from equation 10, we have dt by dx equal minus q dot divided by kx, and equate that to 0. Then we will get T max equal to Q dot L divided by HA plus Q dot divided by 2K L square plus TA, which is similar to equation number 11. And this is the answer for this equation and this exercise. And then the maximum temperature occurs at the insulated side of the wall. Now we have a plain wall with a thickness of 2.5 centimeter, and we have heat generation corresponds to 3 times 10 to power 4 watt per meter cube, with a thermal conductivity of the wall as 1.5 watt per meter Kelvin. One of the sides of the wall is insulated, as shown in this figure, and the other wall is exposed to convection, where we have fluid on the other side at temperature 30 degrees Celsius and a heat transfer coefficient of 15 watt per meter square Kelvin. Now estimate the temperature at the adiabatic wall, at the insulated wall, and the wall faces a fluid boundary with, and then also what is the heat flux of at the convection walls. And that means we have to find the values of temperatures. Again, our equation d squared t by dx squared plus a q dot divided by k equal to 0 can be used again for this wall for a one-dimensional heat transfer in the x direction. If we apply equation 9 for the convection wall side, T sub W equal Q dot L divided by H sub A plus TA, which represents the wall temperature at the convection part. And if we substitute these values of L, Q dot, H sub A, TA, then we will get a temperature of 80 degrees Celsius at X equal to L at the wall which faces the fluid, the convection part. And if we apply equation 12 for the insulated wall side, and that means we have X equal to 0, then T max equal Q dot L divided by HA plus Q dot divided by 2K L squared times T sub A, which is represented by equation 12 as we have shown that in the previous example. If we substitute the values of the temperatures and Q dot, thermal conductivity, thickness, T ambient, and heat transfer coefficient of the fluid, then we will get T max equal 86.25 degrees Celsius. And to calculate the heat flux at the convection boundary, Q equal to H sub A times TW minus TA. Then we will get Q of over A divided by A equal to the heat flux. If we substitute the values for H sub A 15 watt per meter square Kelvin times T sub W minus TA, then T sub W it has been already calculated as 80 degrees Celsius. Then Q divided by A, which represents the heat flux, is equal to 750 watt per meter square. We have arrived at the last part of the present video for today's lecture, which is related to closure of the content which we have introduced within this video, we passed through one-dimensional heat conduction with heat generation inside that wall. We applied the adiabatic and convection boundary condition to a wall with some work-out exercises. We have some useful resources in the description box. You may make advantage of that. And I would like to thank you for watching and following this channel. Your valuable support is really appreciated. And if you think that the content of the present video are useful to you and others, please subscribe and share it with others to fulfill the requirements of the objectives from creation of this channel. See you soon. Bye-bye.